Hey guys, today we are looking at notes for factoring with the greatest common factor, or a GCF. GCF is going to be our first step in all of our subsequent factoring problems. It's always going to be the thing we check for first because it's the most simple but also the most useful factoring method that we'll look at. So for today, what we're looking at for 4-box notes, we're going to go ahead and jump into box number 1 here with our definitions. The greatest common factor, or the GCF, is what I'll go ahead and continue calling that because that's a whole lot faster than saying greatest common factor. It's a monomial, so it's a single term, that evenly divides each term in an expression. Now, that definition actually is just the definition of what is a common factor for a polynomial or for an expression. The greatest common factor, specifically, it's the term that has the biggest number, the largest number, and the highest degree variable in common amongst all of the terms of that polynomial or of that expression. So it's the thing that is in common between all of them. So it's a common factor, like we looked at yesterday with the gizmo that we're working on, that we're looking at common factors, so things that multiply into all of the terms of my expression. It's the biggest one of those that also has the highest degree exponent variable in common amongst everything in my polynomial. So in box 2, we're going to look at just identifying what is the GCF between a set of numbers or a set of terms. Now, it could be between just 2 things. It could be between 3 things. Eventually down the road, like in Algebra 2, we'll do GCFs with 4-termed polynomials and 5-termed polynomials, a whole lot of them. So it's going to be a skill that we continue utilizing moving forward beyond this class specifically, but into a little bit in geometry, but again, quite a bit in Algebra 2. So when we're finding the GCF, I have 2 different methods of doing this for numbers. Now, I know on the gizmo yesterday that you guys were working on was kind of really going hardcore into factor trees. So I'll show you what that looks like for identifying the GCF from a factor tree. And then I'll show you another method depending on, whether that made sense for you or not. So if I'm trying to find the GCF of 24 and 32, meaning I'm trying to find the biggest number that multiplies into both 24 and into 32, is what a GCF is in this case. If I'm going to do the factor tree method here, this is more similar to the gizmo from yesterday. I'm going to start by just making my factor tree for each of those 2 terms, each of those 2 numbers. So if I do my factor tree for 24, it could be set up as maybe 4 times 6. 4 is 2 times 2. 6 is 2 times 3. So my prime factorization for 24 would be 2 times 2 times 2, which is 2 to the 3rd power, times 3. If I did the same thing for 32, depending on how you want to visualize that, could be 4 times 8, which 4 is 2 times 2, 8 is 2 times 4, and then this last factorization here, 4 is 2 times 2. So I have 1, 2, 3, 4, 5 2's and 32. And then 2 times 2 times 2 times 3 is my factorization for 24. So when I'm looking for my greatest common factor, I have to look and see at everything that each of those factor trees has in common. So looking at 24 and 32, I have 1, 2, 3 2's in common, and that's it, right? Because my 24 also has a 3 there, but my 32 doesn't have that 3. My 32 has 2 more 2's, but my 24 doesn't have 2 more 2's as well. So those 3 2's that I have highlighted is my greatest common factor. So if I wanted to write this up, my GCF would be, if I'm doing the factor tree method, 2 times 2 times 2, which is 8. 2 times 2 is 4, times 2 is 8. So that's option number 1. If you really liked that factor tree method and it's kind of old reliable, it might take you a little bit longer, but it will get you the answer for sure. Another method you can do, and this is kind of what my brain does. I'm showing you kind of the full process of it. And as you as you gain more experience with these, the easier these factors will be to find for you. But what I like to also do, another option for us, is to write out the factors of 24 and the factors of 32. So I'm just looking at all the different things that multiply to get into 24, all the different things that multiply to get 32, and I just compare that list, those two lists together, and find what my biggest number is. Now again, as you get better at this, your brain will kind of do this automatically, or kind of, maybe with a little bit of thought. So if I list out all the different factors of 24, all the different ways that I can multiply 24, do this in green here. 24, I could do 1 times 24. I could do 2 times 12. I could do 3 times 8. Or I could do 4 times 6. So all of those different numbers there, not in order, and it's kind of a mess. Some people like to do it in order. Some people will just list them all out. Those are all the different factors of 24, at least the whole number factors of 24. Those are all the different things that multiply to get 24. So if I did that same thing with 32, 32 could be 1 times 32. It could be 2 times 16. It could be 4 times 8. And that should be it. Because then as soon as you get the other side, 8 times 4, yeah, sure, 16 times 2. But those are all my unique factors. So now that I have that full list of all my factors, I just have to compare those lists together and see what's the biggest number that they have in common. And in this case, of course, it's 8. 8 is the biggest number that is in both of those two lists, and 8 is the GCF. So 8's the biggest number that they both have in common. So it's really up to you. Some people can just look at those two numbers and see what it is. You might have to write some stuff down. It really depends on what the two numbers are. Two bigger numbers like this, it might be something that you might want to write down. If you see something like number 2, where we have just 4 and 24, well, the only factors of 4 are 1, 2, and 4. That's it. So, and we know that 4 is a factor of 24, so then the thing that they have in common is going to be 4. So it's a little bit easier for us to see with smaller numbers, or maybe if one of them is a small number and the other one is a bigger number, you can are much more limited in terms of what the factors are for 4. So that's another way to look at it. So kind of getting into I already started talking through the number side of number 2 here, which now we start having both numbers, both coefficients and variable terms. So now it gets to be a little bit more complicated, because for our number side of things, for the coefficients, our 4 and our 24, it's still the same process of what we were just looking at. So we're still just looking at what is my biggest number that is a factor of both 4 and 24. So for that aspect of it, that side of things, like we already talked about, what they have in common is 4, right? 4 is a factor of itself. 4 is also a factor of 24, so 4 is what they have in common. The trickier part here is the variable side of things. So when we're looking at the variable side of things, we're looking for the biggest exponent. So since they both have the same variable, x, we have to look and see what's the biggest variable, what's the biggest number, or most number of x's that they have in common. So if you need to, you can write this out. If you want to write 4x squared as 4 times x, and then 24 is just 24 times x. And you can look and see this first one has 2 x's, but this second term only has 1 x. So they only have a single x in common. So my GCF, even though we want it to be the greatest thing possible, it's only what they have in common. And in this case, the only thing they have in common is a single x value. The 4 they have in common for my coefficients, but then x is my only thing that they share between those two terms. So my GCF here would be 4x. And I forgot to box this in. My GCF for number 1 was positive 8. Okay. Now looking at number 3, this is much more tricky, because I have 3 different terms that I'm looking at to find my GCF. Now the nice thing is the process doesn't change. It's just that we're looking at If it's going to be common, it has to be common between all three of them, not just between any two of them. So you have to look and see what are the common factors between all three of these terms and not just the two of them. So depending on which of those skills you liked, whether you were a write out the factors person or you were a prime factorization person, so a factor tree person, it doesn't really matter on how you want to go about doing that. You're just looking to see at what are the things that they have in common. What's the biggest number that they have in common? So if you want to, which we can do the factor tree just so I can show another one, because otherwise you're just listing out factors. So 63 is what? 7 times 9. 9 is 3 times 3. 56, that's 7 times 8. 8 is 2 times 4, which is 2 times 2. And then 21 is 7 times 3. So you can see, and I even naturally did this just because I see what they have in common. All three of them have 7 as a factor. Now, 63 and 21 also share a 3 between the two of them, but 56 doesn't have any 3 involved. So even though 3 is common between two of them, it has to be what's common between all three of my terms. So for my GCF for number 3, the number for the GCF is positive 7. Now, moving on to the variable side of things, my 3 different terms each have a k value. K is my variable here. And for the exponents, my first term has 4 k's, right, k to the 4th power. My second term has k cubed, k to the 3rd power, so I've got 3 different k's multiplied together. And then my last term has k squared, k to the 2nd power, 2 k's multiplied together. So again, if you need to write this out, k, oops, I'm going to use a different color here, we'll use green. K to the 4th is k times k times k times k. I'm going to move that over here. Oops, didn't get all of it, did I? Let's try again. Scooch you over. The 4 didn't come along for the ride, so I'll just go ahead and move that the old-fashioned way. So this middle term, since it's k cubed, I'm just going to erase this stuff. Here we go. That's just easier. K cubed, that's 3 k's multiplied together. Should have chosen a different variable and not used 3 k's. And then 2 k's for my last one. So looking at what's in common between them, I have 1, 2, and that I've run out of k's for my last term. So I have 2 k's in common between all 3 of my terms. That's the most number that all 3 have. So my GCF here, I would have 2 k's, so that would be k squared. So a little tricky, a little complicated, as we get to be 3 terms to work with, but it is what it is. It's something that process-wise is not overly difficult. It just can be tedious and or time-consuming, depending on how quickly you're grasping this. But that would be my GCF there, 7k squared. So that's finding GCFs. Just identifying what the GCF is between different terms. In box 3, we're now moving into factoring out a GCF. Now, this, for some of us, will make more sense because what we're basically doing here, factoring out a GCF, is like undistributing a term back out of a parenthesis. So we're looking at what they have in common and then taking that out of both of those 2 terms, or all of those terms in my polynomial. So you first have to identify what is the GCF. So for number 4, we have 16r to the 4th power minus 28r as my polynomial. So looking at my 2 numbers, 16 and 28, well, 16 is 4 times 4, 28 is 4 times 8. So 4 is definitely the GCF for my number. So I'm going to go ahead and just jump to that. So my GCF is 4. And actually I'm going to bump this up a little bit so it's easier to read. So my GCF is 4 for my number. Between my 2 terms, they both have r. They both have an r in common. But my second term there, my right term, only has r, not r to the 4th power. So it doesn't have anything else. 4r is just going to be my GCF here. Now, since I'm trying to factor out that 4r, what I'm basically doing now is pretending like this is going backwards from distribution. If 4r is what I distributed into a parenthesis and I ended up with 16r to the fourth minus 28r, I have to now figure out what would that parenthesis have to look like. So you can think of that's the way I like thinking about it. You could also, technically, you could divide both of these if you want to do it that way. 16r to the fourth divided by 4r, and that gives you the first term. Negative 28r divided by 4r is also going to give you the same thing. But I prefer thinking about it as what would I have to multiply 4r by to get back to my original problem. So 4r to get 16r squared, or sorry, r to the fourth power, 4 times 4, I didn't mean to change the color there. 4 times 4 would get me back to my 16. I have an r to the first power on the outside, and I need an r to the fourth on the inside. So r cubed. Because if I multiply those two terms together, like I was distributing, I would get 16 out front and r to the fourth power for my variable. I want to make sure this is still a subtraction, so I'm not going to change that value at all there. But then to get 4r times something to give me 28r, well, the r is already there, so I don't need to multiply by a variable. All I need is to change that 4 into a 28, so I need this to be, it's a goofy looking 7. Let's try that again. 7. Because if this was a distribution problem, if it was a multiplication problem I gave you on the quiz from before spring break, you would end up with 16r to the fourth minus 28r. You would just multiply your 4r times 4r cubed, 4r times negative 7, and you'd get back to that original polynomial that we started with. And that's basically what factoring with a GCF is. I'm just working backwards from distribution. So if I try that on number 5, if I've got negative 20x to the second power minus 24x. My GCF here, I see that they're both negative, so I do want to make sure I bring that out for sure. 20 and 24, between those two things, this might be one that you write down. 20 is 4 times 5. 24 is 4 times 6. So once again, we're looking at a 4 that they have in common for my coefficient side of things. Negative 4 times 5 gives me negative 20. Negative 4 times 6 gives me 26, or sorry, negative 24. So that's my GCF for my number. In between my two terms for my variable, x squared and x, they have an x in common. So if I'm trying to work backwards from distribution. If my negative 4x is on the outside, this first term to get multiplied by, to get back to negative 20x squared, I need a 5 to make my negative 4 into a negative 20. And I need another x value in order to get back to x squared. For my second term, negative 4 times a positive 6 gets me back to my negative 24. And then x is already there, so that's all I need, 5x plus 6. So that would be my final answer. That's my factored version of that original binomial. All right, last one here in our factoring with GCF box 3. Now we're dealing with a trinomial, so a 3-termed polynomial, and we're trying to factor my GCF out of all 3 of those things. So we're trying to factor out my GCF for this polynomial, which means we have to look at what's in common between all 3 terms. So 35, 50, and negative 30. Just looking at those, my brain sees that they're all multiples of 5. So that's probably what I'm going with. So 35 would be 5 times 7. 50 would be 5 times 10. 30 would be 5 times 6. So that's 5 times 7 they're both prime numbers there for 35. So there's not going to be anything else in common between 50 and 30 as well. So 5 is definitely going to be my GCF for my number side of things. So 5 is definitely my GCF. Between my 3 terms for my variables, z to the 6th power, z to the 4th power, and z cubed, they have 3 z's in common. Because if I listed out all of them, I have 6 z's in my first term, 4 z's in my second term, 3 z's in my third term. They have 3 in common between all 3 of them. So z cubed is going to be my variable side of the GCF. So 5z cubed is that GCF. So going back to the inside of my parenthesis here for my factorization, again, inside the parenthesis is what I have to multiply my GCF by to get back to my original. So 5 times 7 would give me 35. If my z to the third power is my GCF on the outside, I need 3 more z's to get back up to positive 6. So that's my first term. For my second term, 5 times a positive 10 would get me back to positive 50. If I've got z cubed and I want z to the fourth power, I need another z on the inside. And then for my last term, 5 times negative 6 would get me back to a negative 30. It already had z cubed, so it's already there. I don't need to multiply by a z at all, so that would be the end of my polynomial. I'll go ahead and close my parenthesis. So z to the third, or 5z cubed times parenthesis z 7z cubed plus 10z minus 6 would be my final answer there for number 6. All right, last box, box 4. Now we are putting it together with what we looked at right before spring break last 2 weeks ago, with our last section being 7.4 that we covered before our quiz, which was solving using ZPP, so zero product property. So now we're solving using GCF, which really we're still utilizing ZPP, so I guess we could just say solve using GCF and ZPP, zero product property. So what we're doing here now, we're trying to solve this polynomial. We have the equation for number 7 as 2y squared minus 10y equals 0. And if we were just given that equation before we knew what we know now, we would try and isolate my variable, get my y by itself, and then fail miserably because y happens in 2 different places and I can't combine them together because they have different variables, so I'd have no idea what to do. You'd panic and have a very, very stressful evening of trying to figure it out and doing a whole lot of Googling. But now we're all happy because we know what to do, right? We have something on the left side here. It's set equal to 0, so I'm dealing with the left side. Because remember, in ZPP, we want things to multiply to 0. That's the Z in ZPP. Zero product property means if I have things that multiply together that equal 0, one or both of those factors, or any of those factors, at least one of them, has to equal 0 in order for that to be true. So what I'm going to try and do here for number 7 is factor that left side of my equation using my GCFs that we just learned so that I have a product. Because in order to use zero product property, we have to have a product that also equals 0. So we're going to try and force that to happen. So in number 7, 2y squared and negative 10y, my GCF between 2 and negative 10 is definitely 2. They're both even numbers, so they have a 2 in common. And looking at my variables, they also both have a y in common. So I can have 2y as the GCF. If I was going to then factor that out of my polynomial, just like I did in box 3, what I would have to multiply 2y by to get back to 2y squared, is just a y. I don't need to multiply any numbers because my 2 is already there. My y times my y would give me y squared. For the second part of my polynomial on the inside, my parenthesis, 2y times negative 5 would give me negative 10. And then my y is giving me y again. So y minus 5 would be my parenthesis. Now that still equals 0. And now this looks like a problem that we solved in 7.4. We went through and solved these because anything that multiplies together to give me 0, I can just set each of those factors equal to 0 individually. So 2y equals 0. Y minus 5 equals 0. It's a weird looking 5 that got all interconnected. Let's try that again. That's better. And then I'm going to solve each of those independently. So if I go through and divide by 2 on both sides, that gives me y equals 0 is one of our solutions. I add 5 on both sides, and we get positive 5 as my other solution. So those are my 2 solutions for number 7. We'll go ahead and try the same thing with 36 or with number 8. So number 8 is 6n squared equals 36n. So the issue here is not only am I have an n squared and an n term, I don't have that 0, that z in ZPP. I don't have something set equal to 0. So the first step that we have to do here is actually going to be rearranging my equation so that I have 0. What I want to do for these problems is move everything over on one side of my equation so that the other side is 0. So I'm going to go ahead and just subtract 36n from both sides to move that term over. That would give me 6n squared minus 36n equals 0, because there's nothing left over on that right side, which we know the mathematical representation for nothing is 0. So now I have something that looks more familiar to me. I can start with that left side, 6n squared minus 36n, find the GCF and factor that, and then I'll have a product that I can use ZPP on to solve for my individual solutions. So looking at what's in common between 6n squared and negative 36n, well, that's definitely, at least to me again, obvious that 6 is what they have in common. So 6 is both a factor of 6 and 36. And then for my variables, n squared and n squared and n, those are n's. They have the n in common, but my second term only has a single n, so I can't take 2 of them because it's not in common. So 6n is the GCF. So if I go ahead and apply that, let's do a little solving, or a little factoring now. 6 times, well, we don't need anything else to get me back to 6. N times n would get me back to n squared. So I'm good there. My second term, I would have to multiply by negative 6 in order to get back to negative 36n, because 6n times negative 6 would give me negative 36n. That is still equal to 0, so that would be my factored version of that same equation. So from here, again, I'm going to set each of my factors equal to 0. So 6n equals 0, and n minus 6 equals 0. And then I'm going to go ahead and solve for n. So divide by 6 on both sides to get 0 for my first solution. Add 6 on both sides to get n equals positive 6. All right. That's all I got for you. I don't know what's going on with my computer here. Stop it. That's all I got for you. So your homework is the Factoring a GCF worksheet. So it's posted on Classroom. Those who are in person have a hard copy of it. But it is a worksheet that is just factoring GCFs. So it's all problems like box 3. So I just give you polynomials. You have to find the GCF and factor it out. So as always, if you guys have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting me know. Otherwise, we'll see you soon. Have a fantastic day.